So sometimes we run into a situation where you have equally valid Lewis structures that could be drawn more than one way. And this gives us a condition we call resonance. So let's take a look at sulfur dioxide, a molecular compound. And let's just go through this. If we look at the top of the group for sulfur, we see it has 6 valence electron. Oxygen is in the same group, so it also has 6. And so that gives us 18 valence electrons. Okay, so these are valence electrons. And the central atom will be sulfur. So we can go ahead and we can draw our structure and we can count up the number of electrons in our Lewis structure. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I have 18 valence electrons. I've used 20 to draw my structure, so I'm 2 over and I need to make another bond. So make a bond. And that means we need to make a double bond, and we've got 2 opportunities to do so. So make a bond, okay? And we're going to make a double bond. So we would remove 4 non-bonding electrons and replace them with 2 bonding electrons, and that would get us to 2, 4, 6, 8, 10, 12, 14, 16, 18, and that would be our structure. But couldn't we have put this double bond instead of between sulfur and this oxygen, sulfur and the oxygen on the other side? And the answer to that is yes, we could. So I'm going to go ahead and just pop these in. And so you can see that we could have put the double bond with either the sulfur and this oxygen or the sulfur and this oxygen. Whenever you have a situation where you have 2 equally valid Lewis structures with multiple bonds on one side or the other, you have a condition that we call resonance. And resonance is simply a condition when you have more than one equally valid Lewis structure that you can write for a particular molecule. The actual electronic structure is not represented by any one of the structures, but the average of all of them. So we think of averages in terms of colors. If we take a blue color, we mix it with a yellow, we get a green. So this would be indicative of a resonance structure. One of the things we can say about resonance structures, and again, resonance structures where you can have equally valid Lewis structures, I could have the double bond over here where it's indicated, or I could put the double bond between sulfur and the other oxygen. The true structure is an average of both structures. So you could just think of the electron distribution in the double bond as being stretched out across both oxygens. And one of the things we would say about resonance structures is that they are an average of both structures, or of all the resonance structures, average of all resonance structures. So the true structure is a blending of both resonance structures, or an average of both resonance structures. So there's actually a problem with our resonance structure if we look at formal charge. So let's go ahead and calculate the formal charge just like we did for carbon dioxide. So the formal charge on this oxygen has 6 valence electrons. That's just the number at the top of the group. It's got 4 non-bonding electrons, and all 4 of these non-bonding electrons are assigned to that oxygen. And it's got 2 bonds, or 4 bonding electrons. It gets half of those, or you could just count the number of bonds to this particular oxygen, and that's 2. So that's 4 plus 2 is 6, and so the formal charge on this oxygen is 0. We can do the same thing for sulfur, and so sulfur has 6 valence electrons, just like oxygen does. It has 2 non-bonding electrons in this particular structure, but it has 2, 4, 6 bonding electrons. Half of 6 is 3, which is the same as the number of bonds. 2 plus 3 is 5. 6 minus 5 is plus 1. So the formal charge on this sulfur is plus 1. If I go over here to this oxygen, I have 6 valence electrons, just like the other oxygen, and I have 6 non-bonding electrons. 2, 4, 6 plus half of the bonding electrons are just the number of bonds, which is 1. And that 6 plus 1 is 7. 6 minus 7 is a minus 1 formal charge. Now, oxygen is actually pretty happy with negative formal charges. Sulfur is sort of electronegative. It's not going to be thrilled with this positive charge. So the question is there a more stable Lewis structure that we could draw that is more reasonable based on formal charge? And the truth of the matter is, yes, we can have this oxygen donate both of these electrons to the bonding area in here, and that would give us this. It would give us a double bond to oxygen over here, a double bond to oxygen over here, and we've reduced the number of non-bonding electrons. We've still got a non-bonding pair of electrons on the sulfur, but let's go ahead and let's count the number of electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. I have 18 valence electrons. I used 18 electrons to draw my structure, none left over. Now let's calculate the formal charge on each one of these atoms. I've got 6 valence electrons on this oxygen minus 4 non-bonding electrons plus 2 bonds, or half of 4 bonding electrons, which is 2. That's 4 plus 2 is 6. That gives me a formal charge of 0 over here. This oxygen looks exactly like this oxygen, so we would calculate a formal charge of 0 over here. Let's try sulfur and see if we can get rid of that positive formal charge using this Lewis structure. So it's got 6 valence electrons, it's got 2 non-bonding electrons, and it's got 1, 2, 3, 4 bonds, or 8 bonding electrons. Half of 8 is 4, same as the number of bonds. 2 plus 4 is 6. 6 minus 6 is 0. So we've got a 0 formal charge on all of our atoms. And remember, with formal charge, you're trying to get as close to 0 as possible on all your atoms, and if it's a molecule, it actually has to add up to 0. It adds up to 0 here, but because we've reduced the positive formal charge to 0 and we've increased the negative formal charge to 0 over here on this oxygen, our formal charges are lower for this structure, and so this structure is the more reasonable structure based on formal charge for sulfur dioxide. So even though we could draw a resonance structure where we didn't bust the octet rule, notice that I have 2, 4, 6, 8, 10 electrons around sulfur on this structure, and so I have broken the octet rule. There are some elements in which I can exceed the octet, and we're going to talk about that right now. All right, let's do a resonance structure for a carbonate ion, and well, I'll demonstrate that it is a resonance structure. So if we go to the top of the group, we know that carbon has 4 valence electrons, oxygen has 6 valence electrons, there's 3 of them. But keep in mind, there's a 2 minus charge. So this is going to be 4 plus 3 times 6. And because of this 2 minus charge, we have 2 extra electrons, so we have to add 2 electrons. So that's going to be 3 times 6, which is 18, plus 2 is 20, plus 4 is 24 valence electrons. Oops, can't spell. All right, central atom is carbon. So here we go. So there's carbon. I'm just going to go ahead and plop the substituent atoms around carbon. I'm going to give them everything they want. Now I'll go ahead and use bonds here just to make things a little bit neater. So we've got 2 electrons for each of these bonds that I've put on oxygen. We'll go ahead and use dots. And so I've got dots, 8 electrons around each oxygen. So that's 2, 4, 6, and don't forget the bond to 8, and 2, 4, 6, and 8, and don't forget carbon, it gets 8 electrons too. 2, 4, 6, 8. Now we count them up. Now here's an easy way to count. I've got 3 oxygens around carbon. Each one of them has 8 electrons. 2, 4, 6, 8. 3 times 8 is 24 plus the 2 non-bonding electrons on carbon. And that means that I've got 26 electrons used to draw my structure. I'm 2 over, so I need to make 1 extra bond. Does it matter which which oxygen I choose? No. And I'm going to go ahead and I'll just choose this oxygen and these 2 electrons. And then so I'm removing 4 non-bonding electrons and I'm replacing them with 2 bonding electrons. So let me redraw that structure a little cleaner. I'll draw it over here. So that's going to give us a single bond to this oxygen, a double bond to this oxygen, a single bond to this oxygen. And one thing you can do is you can use lines, little short lines. Each one of them represents 2 electrons. That just makes your task a little easier because the dots become a little bit cumbersome. So now we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and that is our structure for the carbonate anion. It's got a 2- charge, but could I have put this double bond over here between carbon and this oxygen, or carbon and this oxygen? So the answer to that is yes. And so I could have had a double bond here, single bond here, single bond here, and that would have been my resonance structure. If you'll get, well, I'll go ahead and I'll throw them in. Okay, boom, boom. Now that I can use lines and you guys understand what they mean, this is one of my resonance structures. And then I can have another resonance structure where the double bond is over here. And I'll have a single bond here and a single bond indicated over here. Now, what is the truth about this resonance structure? The real structure is actually the average of all 3 resonance structures. Okay? Each one of these bonds, if I were to ask you the question, and we'll just call that structures, okay, if I were to ask you which one of these bonds is the shortest and the strongest, the answer is all bonds are the same. They are all the same. Okay? They're the same length, so I should throw bonds in there. All bonds are the same length and the same strength. One isn't different from the other. Okay, and that's because what we have here are resonance structures, and there are 3 different resonance structures. What is the truth of this molecule? The truth is that this isn't really a double bond. It's actually 1/3 of a double bond. And this isn't really a single bond. It's 1/3 of a double bond. This isn't a single bond. It's 1/3 of a double bond. The true structure would look more like bond, 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 and ... meaning the electron density is stretched over all 3 bonds evenly. So anytime you have a resonance structure, guys, all the structures are the same. All the bonds are the same. They are each resonance. The true structure is the average of all three resonance structures. Okay, that's what you want to remember. Okay, let's look at exceptions to the octet rule. These are, guys, exceptions, octet rule, exceptions. And there are three big exceptions that we'll deal with. The first exception we'll look at are odd numbers of electrons. This is nitric oxide, very important molecule in biology. It's a vasodilator. We'll look at nitrogen. It's got 5 valence electrons. Oxygen has 6. So this is 5 plus 6, which is an odd number. It's 11 valence electrons. All right, so there's no central atom because we've just got 2 atoms. So I'm going to go ahead and just throw them over here. I'll use a line to represent a single bond, which has 2 electrons in it. And I'll give everybody the octet. Everybody gets what they want. So we've got 2 and 4 and 6 and 8. Terrific. Okay, so let's count them up. 2, 4, 6, 8, 10, 12, 14. Oh my gosh, I used 14, but I only have 11, so I'm 3 over. All right, I can use 2 of those electrons and make another bond, so I could get rid of a pair of non-bonding electrons here, a pair of non-bonding electrons here, and I could make a double bond. But that's still going to give me 2, 4, 6, 8, 10, 12. I'm still 1 over. I've still got 12 electrons in my structure, and it can't possibly be so because nature gave me 11 valence electrons. It did not give me 12. So I have to make a choice as to which one of these atoms gets the extra, gets its octet, and which one has to do without. And the fact of the matter is, as you go across the periodic table in this direction, effective nuclear charge gets higher and what we call electronegativity. Electronegativity gets higher. And in general, electronegativity, guys, developed by Linus Pauling, it's a calculation using electron affinity and ionization energy. And so it's high over here, not excluding the noble gases, because remember, they're happy. They don't want any extra electrons, so this is going to be high electronegativity. This will be very low electronegativity for the very same reasons. Has low electron affinity, low ionization energy. It's easy to pull electrons away. So in general, these guys want the electrons more. Fluorine is the queen of electronegativity. All right, she's the highest on the Pauling scale with an electronegativity of 4. It's just a number based on a calculation, but we're just going to compare oxygen to nitrogen. And between the two, oxygen is further in this direction. So oxygen is more electronegative. Electronegative. So oxygen is going to get its octet, and poor little nitrogen over here is going to have to do without one of its electrons. We call this a radical species because there's an unpaired electron in nitrogen monoxide. It's also known as nitric oxide, and you might think of nitric oxide. Bodybuilders are trying to add nitric oxide into their diets, and the reason is because it's a vasodilator, and so it'll expand the vasculature, and so they can supply their muscles more oxygen, because of the expanded vessels, the expanded arteries, the expanded vessels. Okay, so this is a radical, and whenever you have an unpaired electron in a species, you have a radical, and this will occur whenever you have an odd number of electrons. You have to make a choice between the more electronegative atom and the less electronegative atom. So just to go back to the first exception in the PowerPoint notes, Lewis dot structures that have an odd number of electrons, there's your nitric oxide. It only has 11 valence electrons. We draw the structure. We wind up with 13. So we go ahead, we make a double bond over here, and then we have to get rid of one more. And so we wind up with the radical species, the species with the unpaired electron. Exception 2, Lewis dot structures that have less than an octet around the central atom. BF3 is certainly one of those. If you look at the periodic table, you'll see that boron is in group 3, fluorine is in group 7. So if you count the number of valence electrons, I'll draw that for you in just a second, plus one more. You draw boron trifluoride here, you count the number of electrons, you have 3 times 8, which is 24, plus 2 is 26. So you just remove a pair of electrons from boron, which is what we call an electron deficient atom. Boron would be perfectly happy with 8 valence electrons in the right molecule if it had another substituent atom, but it's also okay with 6. So if I'm drawing boron trifluoride, I look at boron, it's in group 3. Fluorine over here, it's in group 7. So that's going to be 3 plus 3 times 7. 3 times 7 is 21, plus 3, that gives us 24 valence electrons. And so boron is our central atom. I go ahead and I throw my fluorines out there. I'll throw fluorine down here. It's a little easier. And I'm going to give everybody what they want. What do they want? They want 8 electrons. So 2, 4, 6, 8, 2, 4, 6, 8. And 2, 4, 6, 8. Boron wants 8, but it's actually okay with 6. So I'll go ahead and throw these up there. Now just keep remembering that there are 8 electrons around each of the fluorine. 2, 4, 6, 8. And 3 times 8 is 24, plus these are 26. You're going to have to remember that boron is one of those atoms that's electron deficient and in the group, and it only has 3 valence electrons, so we just simply erase those electrons because they don't exist in boron trifluoride. Let's do one more. Let's look at beryllium hydride, this guy over here. Now beryllium is in group 2. It can only handle, it only has 2 valence electrons. We've got 2 hydrogens, each one of those with 1 valence electron. Are we going to have an octet anywhere if I only have 4 valence electrons? No. Best we can do is a quartet. So this is beryllium, and beryllium can only make 2 bonds. And so this is our Lewis structure for beryllium. It's electron deficient. It violates the octet rule. Okay, violates the octet rule by having less than 8. Same thing that boron can do. The difference is that I could have another atom up here and boron would be perfectly happy with 8, but if it only has 3 substituents like this, it's only going to have 6 valence electrons. So you're going to need to remember boron and beryllium as being able to violate the octet rule by having less than an octet. That's the exception. Okay, exception 3 is our Lewis dot structures that have more than an octet around the central atom. And those are at molecules like phosphorus pentachloride, sulfur hexafluoride, sulfur tetrafluoride. And this is actually pretty common for elements in the third period. That means N equals 3 and higher. So N equals 4, N equals 3. All right, let's draw some structures that violate the more than an octet rule. So here's phosphorus. Phosphorus is in group 5, so it has 5 valence electrons, so we'll plot that down. Chlorine is in group 7, so it has 7 valence electrons, and there's 5 of them, so that's going to be 5 times 7. 5 times 7 is 35 plus 5 equals 40 valence electrons. So the central atom is going to be phosphorus over here, and we're just going to go ahead and plop the 5 chlorines around here and see what we get. Okay, we'll give them all an octet, and I'll go ahead and use lines instead of dots. It's a little faster, it's a little easier, less of a bother. And so here we go. All right, so we've got 8 electrons around all of our species. So remember, this represents 8 electrons. I know that might be confusing out there. Each one of these lines represents 2 dots right there. And so this is 8 times 5, which is 40. I used 40. I have 40. There's none left over, so this is my structure. Okay, phosphorus pentachloride. Now notice how many electrons there are around the central atom phosphorus. 2, 4, 6, 8, 10. I have 10 valence electrons, or 10 electrons around phosphorus. That's a bust of the octet rule, because the octet rule says 8. Now here is N equals 3. What do we have available once you get to N equals 3? Well, let's see. N equals 3 means we can have L values of 0, which is an S. Okay. We could have L equals 1. That's a P. L equals 2. That's a D. And that's as high as we go. But what that means is when I get to N equals 3 down here, I get the 3S, the 3P, and remember, the 3D subshell opens up. Now these orbitals for phosphorus, they don't have any electrons in them, so I can plop extra electrons in there and do what we call an expanded octet. That just means I have more than an octet. I can also do it at N equals 4, N equals 5, N equals 6, etc. As long as I'm at N equals 3 or higher, I can expand the octet. Let's do sulfur hexafluoride. This is in group 6. Here's sulfur. It's got 6 valence electrons, plus 6 times 7. That's 42 plus 6. That's, oh my gosh, 48 valence electrons. All right, so sulfur will be the central atom. I'll have a fluorine, I'll have a fluorine, I'll have a fluorine, another fluorine. My gosh, it's fluorine all night and all day, and one more. All right, and each one of those has an octet. Okay, and so here we go. Boom, 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 boom. You got to make that sound when you're drawing them too. Boom, boom. All right, I have 8 electrons around each of my fluorines. 6 times 8 is 48. So I used 48. I don't have any left over. But how many electrons around sulfur? 2, 4, 6, 8, 10, 12. I have 12 electrons around the central atom. I definitely have an expanded octet. I've busted the octet rule by going over 8 electrons. Let's do sulfur tetrafluoride over here. We've got 6 valence electrons and then 4 times 7 over here. 4 times 7 is 28, plus 6 is 34. I'm going to go ahead and throw my 4 fluorines around. Okay, it's getting a little crowded up there, but I think you can see what we got. And then I'll give everybody what they want. What does everybody want? You guys know they want 8. 8 and 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. I have 4 fluorines, each with 8 electrons. 4 times 8 is 32. Well, I have 34 valence electrons. I have 2 electrons that need to go somewhere. Well, they can't go on fluorine. Fluorine can handle a max of 8. They have to go on the central atom, which is sulfur, and that's okay because it's at n equals 3. Here's sulfur. It's at n equals 3, so it can handle the extra 2 electrons. So I have 10 electrons on sulfur, and I have an expanded octet with 10 electrons. I've broken the octet rule, which is exception 3, more than an octet on the central atom. So just to redo sulfur tetrafluoride one more time using the PowerPoint notes, total of valence electrons are 34, 6 on sulfur, and then 4 times the 7 on the fluorines. And then our central atom is sulfur. We build our Lewis dot structure and we count up the number of electrons used. We only use 32, but we have 34. The extra 2 electrons have to go somewhere. They have to go on the central atom. And sulfur is at n equals 3, so it can handle it. All right, so here's a clicker question. Which of the following molecules follows the octet rule? I'm going to go ahead and just do this for you. There's a way to draw the Lewis structure for sulfur dioxide where you don't bust the octet rule. It does not give us the lowest formal charges, but it is an allowed structure. It's just not the most reasonable structure based on formal charge. So we can draw sulfur dioxide where we do not bust the octet rule. Remember, sulfur dioxide, the most reasonable structure for sulfur dioxide looks like this. You got a non-bonding pair of electrons where we do bust the octet rule. Okay, but for the purposes of this clicker question, it is possible to have this as a Lewis structure. So what do we use Lewis dot structures for? We can predict relative bond lengths, relative bond strengths, predict the 3-dimensional geometries in Chapter 9. That's what we're going to do. Relative boiling points, vapor pressures. We'll look at all of that in Chapter 9, and the relative solubilities. For now, this is what I want you to remember. Triple bonds are stronger than double bonds, which are stronger than single bonds. Okay, and this is the way I'll represent them. The little caret that you see right here, this guy right here, the pointy end goes to smaller, less, lower, and the big fatty end over here, this is bigger, stronger, etc., etc. All right, so triple bonds, that should be obvious, are stronger than double bonds, which are stronger than single bonds. I'm going to get out of order here with bond lengths. I think this might make sense as well, and this is a better place for it. Triple bonds are shorter than double bonds, which are shorter than single bonds. So just take a quick look at it. So the triple bond, just think of 3 rubber bands here versus 2 rubber bands versus a single rubber band. So this would be shorter and this would be longer. So if I were to put this all together, I would say single bonds are longer and single bonds, we're sticking with single bonds are weaker. They're weaker than double bonds or triple bonds, all right? So single bonds, longer and weaker. Triple bonds, shorter and stronger. So when you're comparing bonds in a molecule, look at whether you have a single, a double, or a triple.